Thank you. I'd like to acknowledge my colleagues that are contributors to the work that I will present, and I've listed them here. So if we want to understand what sort of atmospheres to expect around ocean exoplanets, oceans, what sort of biochemistry in their ocean, for oceans that have enough water to have a high pressure ice layer separating the ocean from the rocky interior, we need to introduce a lot of hydrophobic chemical species, salts, which would actually introduce a lot of crystal structures like clathrate hydrates, filled ice, salty ice, that may actually fundamentally change our understanding of how material is being transported along high pressure ice mantles. So I wanted to make a point here that clathrate hydrates have very different characteristics than pure water, and we've known this for quite a while. What happens at even higher pressures beyond 1 GPa? Well, some filled ices, for example, that form after clathrates, well, basically don't dissociate, but they dissociate and restructure into filled ice, they can withstand pressures up to 100 GPa, spanning the entire high-pressure ice mantle. So what are sort of characteristics do they have? So we looked at MD simulation. We did an MD simulation for filled ice of methane using the software CP2K, and we used that MD simulation to get the vibrational spectrum of the crystal structure of filled ice, and I just wanted to make a point. These are the results we got for the heat capacity. So this would be the heat capacity for methane-filled ice compared with heat capacities for pure water. We see that it almost sits on the Dulong-Petit value, which would suggest that filled ices have a very low Debye temperature, and this weird behavior of clathrate seems to propagate also into the filled ices, and we really need a lot more work done in order to understand how they influence the interior dynamics and mass transport of ocean exoplanets when you have a high-pressure ice mantle. So if these crystal structures that I mentioned actually exist in the interior, a key question is what sort of solubility do they impose on the overlying ocean? It's very important because it will tell us what sort of chemistry to expect in the ocean, what sort of atmosphere would form around such planets. And these solubilities are not very well known. So we took advantage of data that is known from the chemical literature on hydration shell energies, and we used the Kramer's theory for Brownian particles to relate the solubility of CO2 in the liquid to the solubility of CO2 in clathrates. And I forgot to mention that what I want to concentrate on a very specific problem, where you have an ocean where basically the seafloor of that ocean is clathrates rich in CO2. So we built this theory that could actually tell us what the solubility of CO2 in the liquid would be when in equilibrium with clathrates. And when we compare this theory with experiments at low pressure up to a few hundred bars, our model is the blue curve. It goes through experimental data pretty well, and we see a very distinct behavior where the solubility actually increases with temperature, very different when clathrates are not part of the problem. What happens at higher pressure? What happens at the actual seafloor? That's a really big problem because we don't have direct information for the solubility on the seafloor at a pressure of 1 GPa. We can only infer that data from melting curve depressions. So we took data from Bollinger et al. 2013 for systems saturated in CO2 and tried to infer what sort of solubility you would have when in equilibrium with clathrates. And it's a very delicate problem. If you assume an ideal sort of solution, you get this green shaded area. If you don't assume ideality and you consider the fact that and you can correct for activity coefficients, you get this red shaded area. And the model I showed before with Kramer's theory is this black curve, and it sits very nicely on the continuation of this inferred data. So what we generally know from this modeling, we only use this model to make interpolations. It's very, very important. These models are not good to make extrapolations. The experimental data is very, very important. But what we generally know, when you're in equilibrium with clathrates, the solubility is not a strong function of pressure, unlike when you use Henry's law, for example, and it is reversed with temperature. It increases when the temperature increases. This is what clathrates do when they're in the system. So that's a very important thing to know, the solubility, because if you want to consider the pH of an ocean, you basically want to solve this set of equations, and you have 5 equations. You need a variable to constrain the system because you have 6 variables. And for these particular planets, if you have a seafloor that's composed of CO2, it's an open system. So if it becomes unsaturated with CO2, CO2 will enter the ocean because the clathrates will not be stable. They will keep the ocean saturated. So your solubility is basically what's governing the pH of the ocean. Now, here the charge neutrality equation that I've written seems extremely simple. It's not true for Earth, where you have a lot of interesting ions dissolved in the ocean. And I want to touch on basically explain why we think it may have this simple form. So recently there's been a lot of studies that have been published on what happens to brine solutions at very high pressure. And it seems that at very high pressure, the end result is very different than from low pressure, where the salt is exsolved out of the structure. In very high pressure, where I6 and I7 are concerned, ions dissolved in the liquid actually become incorporated as interstitials in the voids of high-pressure ice. Journou et al. Studied the system, Frank et al. And other studies. And it's more correct for I7 than for I6, though. But another interesting experimental result is that, and I'm talking about a paper published by Frank et al. 2008, if you take such a high-pressure ice where it has interstitials within its voids of ions of salt, when you increase the pressure to 500 K, it seems like that the ions are exsolved out of the ice and form pure grains of dense salt. Why is that important, and how is that? What does that imply for ocean exoplanets that have a high-pressure ice mantle? So we solved for the thermal profile. Let's say this is the bottom, this is the sea floor, and then you have high-pressure ice. This is the thermal profile in the high-pressure ice, I6 and I7. And this condition that I've written here is basically saying that if this condition is true, which for these planets is true even if you have tiny fractions of rock in the planet, then basically this is a scaling for the thermal conductivity and the temperature gradient of the melting curve, that the bottom of the ocean, the seafloor, is actually constrained to the melting temperature, the melting curve of high-pressure ice. But being constrained to the melting curve of high-pressure ice places a constraint on your ability to conductively cool. And what this means is that high-pressure ice that is upwelling would at some point tend to melt and basically discharge its hot water into the ocean. But if you're not basically melting your entire ice mantle and you're in a steady state, then at a lower temperature you have to recondense. So I want you to have this picture in mind where you have an ocean that's discharging, that you have high pressure ice melting, discharging water into the ocean, and then recondensing, creating a new seafloor. Also, another point that I want to show, that contrary to icy moons, because it's very high pressure, adiabatic temperature profiles differ from the melting temperature. This is the melting temperature for I7. They start to diverge into hundreds of kelvins. So if you want to create, for example, a brine pocket and you want to create localized melting, you need to overcome a substantial temperature barrier here. So if you look at isomelting temperatures as a function of pressure, the activity of the solvent, which is water here, that you need in order to create such a huge melting temperature depression, is you need the solvent to have an activity of 0.2. We know from experiments that water does not reach these values. somewhere around 0.7. So you cannot create pockets of brine. So I told you quite a lot of things, and I want to wrap it up in this sort of cartoon, an illustration that explains basically what these experimental data and the thermal profile basically shows us. It shows us that if high pressure ice upwells, it melts into the ocean and forms a new ocean floor, but the new ocean floor that forms, it actually has a high fractionation factor of ions dissolved in the ocean with a new ocean floor. More so for I7 than for I6, and I'll show results for 2 in terms of what it means for the salinity of the ocean. But if this part remixes into the mantle, then when reaching the 500 K threshold, which we find that you indeed reach in the interior, these ions that are interstitials in the ice actually start to dissolve out of the high pressure ice structure and form grains of salt that sediment onto the rocky core. So on the one hand, you have relatively pure water coming out and you have salt coming in, so there's a pump that may actually start to desalinate the ocean over time. And we calculated the time scale for this desalination process. It depends on the fractionation factor of ions between liquid water and high pressure ice and the melting rate. And if the seafloor is I7, the time scale is very, very short. It basically desalinates the ocean very rapidly. If it's I6, which I think is more reasonable, if something like I6, then the time scale becomes very large, but even this large time scale would suggest that you don't end up with more than millimolar concentrations of salt in the ocean. So these oceans could be very rich in volatiles, very poor in salts, which would say that the way that we've written our speciation of the carbonate system properly, and what this would suggest is this pH profile in such oceans. So the pH may go from as high as 3.5 at the surface all the way to around 2 at the seafloor, so it's a highly acidic environment. And if we plot this pH temperature that we have studied on a polyextremophile plot found that we've taken from Kapitz et al., we see that it's a pretty barren region. So it could be that it's a rare environment on Earth, and that's the reason why there isn't a lot of life here. Or it could be substantially a harsh environment for life. But in addition, it's a it basically is an environment that has many stressors. It's not just pH and temperature. It has to combat low salinity, as I've just explained. And the way that you may do that is by introducing an ice cap. And the reason that may help with some of the issues of this environment being highly diluted with salts is with the fact that eutactic freezing within the pores of ice may actually create niches where you may reach higher concentrations that may be more interesting for combating hydrolysis and creating polymerization. And I leave you with these conclusions.
We have a few minutes for questions.
Hey, Steve Vance again, JPL. I guess I didn't understand the mechanism by which I6 exports salt to the bottom. It makes sense to me based on what you said that I7 would do that.
The difference would be in efficiency. So basically the major point would be what is the fractionation, because this actually doesn't depend on I6 or I7, right? In terms of energy balance, you're going to have to melt, and you're going to have to reform a new ocean floor that will mix. The point is how much salt you actually end up with in this region. So the difference is what is the fractionation factor of salts between the ocean and the high pressure ice that would change between I6 and 7. For I7 it would be very efficient because it has larger voids. For I6 it would be somewhat less efficient, but so that's why if I plotted this diagram with a tau d, it's an exponential function.
Got it.
For I7, you'd end up with nothing.
Okay, so I6 just has a lower carrying capacity, which means a
Yeah,
longer time
exactly,
scale.
exactly.
And the key thing about the ocean worlds, or sorry, water planets versus ocean moons, is that the pressures in the water worlds are high enough that you reach this dissolution point at the bottom of the ice. Is that right?
Yeah, I mean, there are several. I mean, first of all, on this arm, so the question, so for this pump to work, you have to bring in relatively pure water and exit and basically sediment the ice, right? If you bring the salt back up, then you don't have a pump. So for ocean worlds, first of all, you have a relatively, you saw the adiabat and the melting, they really diverge. So for icy moons, that temperature is actually, because of the low pressure, is not that substantial. It's a few tens of K. You can easily overcome that and create brine pockets that can certainly migrate up. Certainly if you have like some models for Titan, a mixed ice rock layer, it won't be a problem to basically upwell a brine pocket in this sort of situation. It's very hard to do that. You can't overcome a temperature difference of hundreds of K due to the high pressure. And again, because beyond 500 K, you don't get the ions as interstitials in the high pressure ice, then you can't get the ions back as interstitials and you can't get brine pockets up there as well. So the melting would probably happen somewhere here where the temperature difference between the adiabat and the melting is not that high. So that's why it would work here, but it's not going to work for icy moons, which would explain why you have a lot of salt.
Consistent with some recent literature on the two-phase convection and icy world, or in the moons. Yeah,
exactly.
Okay.
No, it's not contradictory to
Good.
it.
Thanks.
I'd like to encourage those with extra questions to talk to the speaker after the session. So let's thank all the speakers again.